This video will be about logic gates and basic computing using Minecraft Redstone. So let's get into the video. So to start with, we have a basic redstone circuit. And as you can see, the current is not going through to the redstone lamp, but if I flip both levers to be on, then the lamp gets lit up. What is actually here is a simple AND gate. As you can see, if one of the levers is on and the other one isn't, then the lamp doesn't light up. If they're both off, then the lamp doesn't light off. But only if they're both on does the lamp light on. So as I said, this is an AND gate. If both inputs are set to true, then the output is also true. Now I'm going to show you the most simple Minecraft logic gate, the NOT gate. If the input from the lever is off, then the redstone torch is on. If the lever is on, then the redstone torch is off, and that's a simple NOT gate. Using a NOT gate, we can simplify the AND gate to fit into smaller spaces. And next we have a simple NAND gate, aka not AND. With a NAND gate, it has two inputs and one output. If both inputs are on, then the output is off. If one input is on and one input is off, then the output is on, as well as if both inputs are off. Here's a simplified version of the NAND gate. NAND gates will be represented by yellow. Next is an OR gate. The OR gate has two inputs and one output. First the two inputs get inverted, and then they're sent through a NAND gate. Then the output is the OR gate. If one of the inputs is on, then the output is on. If both of the inputs are on, then the output is on. But if neither of the inputs are on, then the output is not on. Here's a simplified version. Next, we have an exclusive OR. It has two inputs and one output. The first input goes into a NAND gate, and this AND gate, which fits right nicely in between these circuits. The second input goes into this NAND gate, into this AND gate, and into this AND gate. This AND gate leads into the final light. But this NAND gate also leads into the AND gate. This leads to if neither of them are on, then the output is off. If one of them is on, then the output is on. But if both of them are on, then the output is off. Next, we're going to build a binary adder. To start making a binary adder, we have to understand binary. So, this redstone lamp is an on state, and on in binary is a 1. This redstone lamp, however, is off, and that is a 0 in binary. Now, when counting normally, you would do 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you increment the next one, or next digit, and then you go 1, 2, 3, 4, and so on. But with binary, there's only two states. So to count in binary, you would go 1, and then you'd try to move to 2, but there is no 2 in binary. So you'd have to increment the next state. And you'd have to do this so on and so forth. And you keep doing this, and as you keep counting, they keep repeating in the same pattern. So here's a good display. For each digit in a decimal number, it's 10 times the first digit. But in binary, the second digit is 2 times the first digit, the third digit is 4 times the first digit, and the fourth digit is 8 times the first digit. Now, how do you do binary adding? So here we have 0, 0, 1, 0, which if I check the book is equal to 2. So 2, and then this would be a plus because we're doing addition, and 0, 0, 0, 1, which is just 1 according to the book. Therefore, what you do is you add them together, so you say basically what is 0 plus 1, and that's a 1. What's 1 plus 0? That's also 1. What's 0 plus 0? That's 0. What's 0 plus 0? That's 0. And that causes this to be added into 0, 0, 1, 1. And if we check, 0, 0, 1, 1 is equal to 3, and that's 1 plus 2. So if you repeat this with every possible 2-bit number, this is the output you would get. And if you saw earlier on all the machines, they all had a sign that looked like this, and this is all the possible inputs. So all the possible inputs are 1, 1, 1, 0, 0, 0, 0, 1, and then has the outputs for whatever those inputs are. So 1, 1 would be both on, and that equals 1, but 1, 0 would be 1 on, 1 off, and that equals off. Therefore, if we head back to our binary adder, we have the top line, the bottom line going vertically on the left side, and then you have the carry, which is like whenever you have to carry a number in regular addition, and then you have the sum, which is what they are added together. And these don't look similar to much, but this looks similar to the exclusive OR, and this looks similar to the AND. Therefore, if we head over to here, this is where it gets into more complex territory. This machine takes 3 inputs, and it's a binary adder, so you can do simple addition. You can elaborate on this further to build a calculator, but I kept it simple for this video. So what happens is the first line goes straight over and into a simplified XOR, and yeah, and also gets put into an adder, which is sneakily put up here. And then the second input goes into this and it also goes into this XOR, and this input goes into the same AND as the other input, and also goes into that same XOR. Now this AND goes over here into, and is also an AND gate from this AND gate, so it's an AND gate of AND gates, the irony. And this gets put into the carry area, so if you were going to continue expanding on this, this is what you would carry over to the next number. And then this input, and then this XOR gate gets put into this XOR gate, and this goes into the sum area, and that was what you would put as a sum. And therefore, if you say want to add 1, then it will come out as with a sum of just 1. And then if you add a second one, then it's going to have a carry of 1, which means that actually it would be 2. So that's 1 plus 1. And you've had all 3 lamps on, then they would both be on, because there would be a 1 the sum and a 1 the carry, and that would equal 3. So that concludes the tutorial I had for today. It went over some logic gates, and most of these are used in extremely complex redstone contraptions. So I hope you enjoyed, like and subscribe, etc.